So we're going to focus on the other type of collision, and that is elastic collisions. I don't know how to spell collisions. I should look that up. That's embarrassing. I should look it up. Hold on. I'm going to look it up. I'll be right back. No, I'm back. You probably didn't know I went away because I paused it, but all right, so I officially, 2 L's, 1 S. Well, at least, there's 1 S. Yeah, 2 L's. Yeah, got it. Okay. I digress. It's getting late. Elastic collisions, keep in mind, these are ones where objects bounce off of each other. And while in the real world, there are really no such thing as a perfectly elastic collision, we can, for introductory physics like this, we assume that all the time. And the example problem we're going to do in a moment is a classic example of that sort of thing. As an overall way of looking at things, so the forces between just say 2 objects, we're just doing one-dimensional right now. So in other words, just for example, 2 objects moving, classic is moving towards each other. Doesn't really matter. It could also be an object moving this way and an object moving this way slower. Well, they could be moving to the left. It doesn't matter. But they're going to collide. And when they do, they're not going to stick together. They're going to bounce off of each other. Which means that if we look at this situation as an example, and we consider this the before, depending on their masses and so forth and so on, let's just say they bounce off and go in opposite directions. So object 1, object 2, and they hit off and they maybe go like this. The after situation also involves 2 objects. And that's going to make these a little trickier because there's more things to figure out. When they combine, there's only one velocity afterwards, and their mass is the combined mass. Or if they start together and break apart, once again, the beginning velocity is the same for both. But here, you have 2 velocities at the beginning and 2 separate possible velocities at the end. You have 2 masses at the beginning, 2 separate masses at the end. So we might start with, obviously, conservation of momentum. But the initial situation will be, say, m1 v1 original, or initially, plus m2 v2 initially, would equal m1 v1 final, so the same object, but now with its new final velocity, plus m2 v2 final. There's a lot of variables in there. I mean, granted, m1 and m2, they show up the same, presumably, over here as they are over here. It's probably the velocities that change. But there's 4 distinct velocities, and that means there's more things to solve with this. Now, as tough as that can make some problems, there is the fact that in elastic collisions, only in elastic collisions, you could also say that the total kinetic energy at the beginning and the total kinetic energy at the end are also the same. And this is only, you can't do it if they stick together. There's energy lost in that to heat. But here, we could say that. But of course, that only helps a little bit in the sense that it gives us a fighting chance. We still have 4 variables, possibly, 5, 6 if you count the masses. So, let me make sure I get this right. V1 final squared plus 1/2 m2 v2 final. Just writing it takes a lot. So, you could conceivably maybe combine these 2 equations. If you had 2 unknowns or more, you might be able to use those 2 equations. In fact, there'll be a separate optional video later. At least it's my intention to make where I show you a very specific case where one object's not moving in the beginning and the other one is. But these can get mathematically, algebraically, pretty complicated pretty quick. But they don't have to be, the concept doesn't have to be hidden in that. The idea here is that the total momentum at the beginning has to equal the total momentum at the end. Now you might get situations where one of the objects, for example, isn't moving at the beginning. So maybe this object isn't moving, it's going to be struck by an object that is moving. Then it simplifies a little bit in that case. But there's no guarantee of that. So let's take a look at a problem that will involve an elastic collision, but I don't think we're going to have to go to kinetic energy here, unless I miss my guess. Let's see what happens. So we have the before situation. I encourage you, implore you even, to write down the before situation and draw yourself a picture. So a cue ball, gives us the mass of it, is at rest on the pool table. So it actually has two parts. Let's take a step back for a second. I've forgotten about this. So there's a before. In fact, we'll call it that. We're going to call it the before. That's not really a thing, but so prior to even worrying about the collision, we have a cue ball that is about to be hit by cue stick. And it's going to be given an impulse. And we need to use that impulse. So we're going back to something we did a while ago, a couple days ago. That impulse, that force applied to the cue ball for a certain amount of time, is going to change the object's, the cue ball's momentum. But of course, before the cue stick hits it, its momentum is 0. So I know that the change in momentum that the cue ball experiences is this. I know that also equals mass of the cue ball, velocity of the cue ball final, minus mass of the cue ball, velocity of the cue ball initial. It's definition of change in. Of course, before it gets hit by the stick, its velocity is 0, so I can say this is 0. And I know this right here is the change in momentum, the impulse, so I know that 2.24 Newton seconds, which, by the way, remember, also comes out to be a kilogram meter per second when you look at it, equals the mass of the cue ball, which I know, times the final velocity of the cue ball after the interaction with the cue stick. So we're looking at this, by the way. The system here is really just the cue ball, because certainly its momentum before does not equal its momentum after. There was a change. So this force by the cue stick is actually an external force the way we're looking at it, which is why there is a change. So solving this for the velocity, that cue ball's velocity after the cue stick interacts with it, is going to be 2.24 Newton seconds divided by the mass of the cue ball, which was 0.165. Kilograms, just kilograms. There we go. So in this case, 2.24 divided by 0.165, that gives me 13.6. So the velocity of the cue ball after being hit by the cue stick is going to be 13.6 meters per second. So that we need that first. And this has come up in an earlier problem, and it's important to note this again. This is only going to happen more and more as the problems involve more and more concepts. Like they might involve energy or kinematics or forces or momentum. All multiple concepts in one problem will be very common. This is the final velocity when we consider the cue stick hitting the cue ball. But when we jump to the next part of the problem, where we have this cue ball moving and it's about to hit some other ball, a stripe. Now, this velocity, which was the final for that scenario, is now actually the original velocity of the cue ball prior to the collision. So we did the before, now we're on the just before. So before it collides, I know the velocity of the cue ball is 13.6 meters per second. We'll assume to the right, so positive. I know the mass of the cue ball is that 0.165 kilograms. Now let's see. I think it's about to hit a ball that is at rest. By the way, you notice they say slides along the table, which is possible if you hit it dead center. That's important because there's no rotational energy. We'll get to that in the next unit. And makes an elastic head-on collision with a second ball of equal mass that is initially at rest. All right, so this one has an original velocity of, let's call this just B for ball, equals 0, starts at rest, and it has a mass that is equal to the mass of the cue ball. So here's the before, and then after, they collide elastically. Now, I have some ideas as to what's going to happen here, but I'm not going to presume. After the collision, there could be possibility of the cue ball bouncing backwards, or maybe continuing forwards, or maybe just stopping altogether. I think it's unlikely that this ball here is going to go to the left. I think we can rule that out. It's probably going to the right. I doubt it's just going to stay there. But we don't know for sure. But certainly there could be a velocity of the cue ball final and a velocity of the regular ball final as well. Neither one of those we know for sure. I don't believe. And we might need kinetic energy here. Let's see. So, they still have the same mass, though. So, conservation of momentum says the initial momentum has to equal the final. And initially, there were two objects, mass of the cue ball, velocity of the cue ball initial, plus mass of the other ball times the velocity of that ball initial, equals mass of the cue ball times velocity of the cue ball final, mass of the other ball times the velocity of that ball final. All those things are there, except some of them are 0. So before they collide, we know that the other ball is stationary, so we're going to call that 0. So what do I know now? Well, I actually know this number, don't I? So I have mass of the cue ball, velocity of the cue ball initial. That's actually a number I could find because I know the mass and I found that original velocity back in the first part. I know the mass of the cue ball. I don't know the cue ball's final velocity. I know the mass of the other ball, but I don't know its final velocity. So I got two things I don't know. I may need to go to kinetic energy then in order to solve this. But let's try this first. I do know the following. I can replace anything that says M with MC or MB. Since they're the same mass, I could replace it with just M. So M VC original equals M VC final plus M times VB final. And I can do that because it tells me they have the same mass. So I could, if I wanted, factor this out. I'm not sure this is completely necessary, but we'll see. It's good to know how to do it anyway. All right. So I know, if I wanted to, I guess, I could know this. I could go M VCO. Ooh, wait a second. Divide both sides by that mass. Interesting. Mass goes away when I do that. Gone. So velocity of the cue ball initially equals the velocity of the cue ball final plus the velocity of the ball final. Now, that's interesting. This would only work, of course, if these masses, like they said, are the same. Okay? But that still doesn't help us completely. What about kinetic energy? So we are going to have to use kinetic energy for this. I lied earlier. Before, only the first ball had kinetic energy. So 1/2 mass of the cue ball, velocity of the cue ball initial, squared, plus 1/2 mass of the regular ball times the velocity of the regular ball originally squared. And of course I know that this is 0, because once again, that other ball was stationary, equals 1/2 mass of the cue ball times the velocity of the cue ball final squared, plus 1/2 mass of the other ball times the velocity of that ball final squared. Well, once again, the masses are all going to divide out, because all these masses are the same. This term, of course, is 0 and doesn't matter anymore. In fact, the halves go away too. I can divide those out. So half mass, half mass, half mass, all gone. So I have the velocity of the cue ball originally squared equals the velocity of the cue ball final squared, plus the velocity of the regular ball final squared. All right, let's try this. So, interestingly enough, I have this statement and this one. Please, 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 if you're not complete, they are not, this is not what you would get if you squared both sides of this. Right? You have to use FOIL. So, let's do that. Let's do this. Let's replace this. So instead of VCO squared, we're going to write VC final plus VB final squared equals VC final squared plus VB final squared. There's a subtle difference here. Now all I did here, by the way, is I replaced this, which is the same as this, with this garbage. Because since VCO is equal to this, I can just stick it in for VCO right here. But like I was mentioning earlier, I can't, this right here, I can't just put the square on that and put the square on that. It doesn't work that way. I have to do the following if you're not familiar with it. I have to do FOIL on them. And when I do that, I will get the following. I will get VC final squared plus 2 times VC final VB final plus VB final squared. And when I multiply these out, that's what I get. That equals, by the way, VC final squared plus VB final squared. So, interesting. I can subtract this from both sides and it goes away. I can subtract this from both sides and it goes away. So, I have 2 times VC final times VB final equals 0. Which is a very curious result. What this means is, by the way, we can divide both sides by 2. Gets rid of the 2 completely. That means that VC final times VB final has to equal 0. What? Well, that means one or both of the, mathematically, it means one or both of these is 0. That means either VC final is 0 or VB final is 0. It's the only way, mathematically, this could be true. So pause and think about it. What's likely here? When the cue ball hits the other one, is it likely that the second ball will just stay right there? I mean, it's not nailed down, right? Is it likely that that one will stay put after the collision? Or is it more likely that the cue ball, upon hitting the other ball, since they're the same mass, will transfer all of its momentum exactly to the other object, and it will be zero. It will stop. So I think if the cue ball comes in and hits the other one, this one's not going to stay stopped. This one, however, I could see that hitting, stopping, and this one going on. Now, if that's the case, both of these can't be zero, right? There's no way both of them are zero, because where would the momentum have gone? But I can see this being true. I don't think in this case this is true. So I think from this, what we're going to take away from this is that the VCF, that has to come to rest. And this is a result, I believe, of the fact that the masses are the same. So the final velocity of the cue ball is zero. Well, wait a second. They have the same mass. And they have to have the same, therefore, if this cue ball stops, the other one has to have all of its momentum. And if it has the same mass, it should have the same velocity that the cue ball had originally. Interesting. So, those of you who like to just grab numbers and multiply stuff, this is an example of where that would hurt you. Because maybe you saw me get this number here and said, wait, that's the answer. Well, stop. You got the answer, dude. It's the number. If you put that in, you're good. You're done. No, you're not. That's the velocity of the first ball. But the physics of it and the math will lead to that conclusion that all the momentum has to go to the other ball. But that's not obvious from this situation. Now, what you hopefully learn from this as well is that if you get stuck in a problem, if two objects collide and they have the same mass and they collide in a head-on elastic collision, the second ball will take on the momentum of the first. Here, I'll give you an example. Hold on. So you probably have seen this device before. They're going to release the ball here, and by the time it gets here, it'll have a velocity, right? It has potential energy here, but it's all going to turn into kinetic, and it's going to have a velocity, a momentum therefore, just before it hits this. But since all of these balls are the same size, the same mass, it's going to stop, pass all of its momentum to this one, which will immediately, by the way, pass it to this one, which will pass it to this one, and will eventually pass it to this one. And of course, we know what happens. That one goes flying off. Now, there's energy lost as it goes, but this is an example of something called a Newton's cradle. And it demonstrates the idea that if the balls happen to be the same and it's a completely elastic collision, that the momentum is transferred, that the object coming in stops and gives all of its energy, all of its kinetic energy and all of its momentum to the second object. So that's not a bad idea to keep in mind as we go through, because you want to understand that. But here is an example of why. And the logical conclusion right here is the trick. Right? The idea that we realize that, and I'm not, just because I wrote this doesn't mean both are zero. At least one of them has to be. And in this situation, the physics says it's got to be the one that came in. The other one is not. Just picture the situation. It's not going to sit there and not move when it gets hit by a ball. And so I'm standing still and not attached to the floor, and someone my size runs at me and hits me. I'm not going to stay there. I'm going to bounce off of them and fly across the room. And they, if it's a perfectly elastic collision, will just stop right there. So, you can see that elastic collisions can be trickier to solve because there's so many different variables involved, like we talked about here. There's all these different things. There's two velocities before, two velocities after, and so on and so forth. They can be a little trickier to solve.